looking at the capillary pressure in a cylindrical channel, we saw that this is determined either by the contact angle or by the geometry. And this is in general true. Capillary pressure will be not only for cylindrical channels, but will be determined by the geometry and by the material. And we've seen using how you can use the hydrophobicity to generate hydrophobic passive valves. In the next part of the lecture, I'm going to show you how you can generate geometric passive valves. I just simply consider a channel with a certain, it gets a bit smaller, and then a sudden opening of the channel. For example, something that looks like this. So I have a solid wall, and I have my liquid, so solid wall, and I have my liquid that comes from here. The system is hydrophilic by nature. And so what will happen, this is liquid. What will happen is that in such a system, we see that the liquid front here will of course fill capillarily. And we'll get a filling like this, and like this, and like this, and it will keep on filling until it reaches this point here. What will happen at this point? We see that the liquid goes, and when it comes here, it minimizes it comes to this wicking point, to the smallest point, where it's first in this shape, and then it minimizes further its energy by getting entirely flat. So I end up with a flat liquid surface here. But for the liquid to continue, what it needs to do, it needs to start increasing its surface, the liquid surface. And it will need to do that until it can assume a shape that looks something like this, with a contact angle theta here. So then I assume this contact angle theta here. So my liquid needs to go from a flat surface and then expand like a balloon until it reaches this surface before it can then again continue its path. And it will start filling again here, like this. But for the liquid to go from the flat position to this position, I can see I need to, my wet area does not change, my dry area does not change, only my liquid-gas interface changes. So I kind of need to blow up like a bubble here, a liquid bubble. And to do that, of course, I need energy. So my liquid, once it's in the flat state, it doesn't want to continue anymore, because if it continues, it needs to increase its surface. So we see that this is actually a stable valve. The liquid will fill to a point where it sees a sudden expansion, and it will stop there. It cannot continue from this point, and it will just be a flat surface. So this is a geometrical valve. The system is hydrophilic, but because of the geometry, the liquid front cannot continue. In 2005, I believe, or 2004, in our lab, I invented a system of that based on geometric valves. Because I needed a system, I would talk to people in the Karolinska Institute, and we talked about protein research, and we wanted to have a system where we had a chip, a top surface. I had two inlet ports, port 1 and port 2, where we would add liquid, and these liquids would have to come together, and they would be somehow mixed together. And at the end of the chip, there would be a spray tip. So what we do is enter the liquid, and then it would be, from here, it would be sprayed out into a mass spectrometer to analyze. So you would, one type of protein, another type of protein, they would mix and react in the mixer, and then you spray them into mass spectroscopy to see how do these two proteins mix and do they interact, yes or no. So we wanted to build a system that did this. The problem with this system is that if you make this in a channel, of course, once I enter my first protein here, the entire system would capillarily fill. And so I couldn't add my liquid 2, or I could, but what happens actually is that, so this starts filling, and it comes at this junction, it starts filling here, and it also starts filling here. So by the time that I have, so there was a liquid front maybe coming to here, so by the time that I would enter a second liquid here, this would end filling, but I would trap a gas bubble between these two. And actually this would stand still, and the whole system would just fill in blue, and it wouldn't do what I wanted. So I had a problem. I needed a system where I could enter my protein sample in 1 and my protein sample in 2, and they would come to the joint point together at exactly the same time before going to the mixer, react, and I could spray them out. So this was the challenge that I was confronting at that moment. And then I thought of the following geometry, and actually we built this also. You can see this geometry on your lecture slides on the PDF. It's drawn in detail. What I did was I made a geometrical valve, something that looks like this. So I had a channel with a certain going narrow and then a certain opening like this. So I knew in this channel here, this was my liquid port 1. My liquid would come to this point and it would stop. And then I built a liquid port number 2. That was here. And I built it so, my liquid port, I'm just making a slide. My liquid port 2 I made symmetrical to this one. So it looked like this. So this is my liquid port 2. So I see if I enter liquid here in number 1, I will get capillary filling until it reaches this point here. And here it will stop. It cannot continue. If I fill liquid in port 2, it will capillary fill. And it would also come to this point and cannot continue, or can it? So if there's only one liquid, for example, only the red one, it stops. If it's only the blue one, it also stops, because they are capillary valves. But however, if these liquids here are here at the same time, and these liquids are intermixable, suddenly you don't have this sudden expansion here anymore. Here the liquid front, they touch each other, and both of them can now continue here and actually flow to the outlet. So I see that my liquid front 1 will wait for the liquid 2 to arrive at the junction before going to the mixer, or the opposite, but they will always wait for each other. This is kind of a fluidic AND gate. Both liquids need to be present before they can move through, and this is just built purely on geometry.